I'm Jonah McLeod in Marketing at Andes Technology, and I will be the moderator. We will have presentations from John Min, who's the Director of North American Applications Engineering at Andes, and Andrew Irving from the Chairman's Office of eMemory and PUFsecurity. Andrew's talk will include an FPGA demonstration of integrating RISC-V from Andes and Puff CC from PUFsecurity. If you have any questions, please click the Q&A icon in a Zoom toolbar or enter your question in chat. At the conclusion, I'll submit your questions to our presenters for their comment. Without further ado, I'll turn the proceedings over to John.
Okay, thank you, Jonah. Just a quick introduction to who Andes is. Andes is a CPU IP company. We've been doing CPU IP for 16 years. We're a public company in Taiwan. We are a founding member of RISC-V Foundation. So we had our own architecture. We switched to RISC-V. We're very active in RISC-V Foundation International and open source community. Quickly, our founders have more than 100 years experience in Silicon Valley in high-tech companies. We are 80% or more engineers. Current to date, we have more than 250 licensees. And as of end of last year, we shipped more than 10 billion SoCs containing our technology and CPU. This year, we hope to have many more. We have to have many more. Here's sort of a large range of processors we have. Processors actually have two dimensions. One is microarchitecture, where N22 is my very small core, N25, and the N series are my microcontroller cores. I have a DSP SIMD line, D and NX series, and then I have the application cores. So one way you get more performance from a CPU is moving to a more complex or higher performance architecture. Second way is going down in geometry and make it run faster. So there's a lot of technologies to pick depending on your application. Here's some of the examples of adoption by the large market. Renesas is making a couple of ASSPs with our cores that are highly scalable and high performance. And they have a lot of feature-rich options. T-Link took our DSP processor, enable processor, and designed a wireless audio solution. Picocom took it to multi-core path, and they're designing a open 5G open cells. And lastly, our high-end vector cores are being used by major companies to do AI and the servers. Okay, so now I'm going to turn it over to Andrew, who will talk to about how to use security, how to add security to our RISC-V course. Okay, Andrew, I'm going to stop sharing and let you share your slides.
Okay, so yeah, I'm just going to give today, again, sorry for the delay, everyone. This is really focusing on security for Andes and RISC-V with PUFsecurity. And we're going to break it down into just a few sections, beginning with a little bit of an overview of eMemory and PUFsecurity, a little bit on the securing the future of computing, and then looking at the 4 fundamentals of chip security. We'll give you a bit of an overview from there, and then we're going to finish with the demo board as well. So let's begin. So eMemory is one of the 10 largest semiconductor companies globally, and it's got about 22 years in the market. It's a pure play IP company. We involve ourselves with the cell level technology as well, partnering with both fabless and foundry customers. It's something we really value as well, the idea of the triangulation between foundry and fabless customers to really see things right through from design all the way through to tape out as well. So with that in mind, taking the technology that's been developed over that time, PUFsecurity was founded a few years ago, and it's a subsidiary dedicated to PUF-based IP, and it's wholly owned by eMemory as well. And what do I mean by building on that technology? Well, within those 22 years, there's been a lot of development, specifically on logic non-volatile memory. OTP and also MTP. For us, the quantum tunneling PUF is the next phase in that development as well. So we have, with the quantum tunneling PUF, our physically unclonable function. The reason we're quite excited about it is it really provides a chip fingerprint, a way of identifying every individual chip. And I want to talk a little bit more about that as well. Specifically with the NeoPUF product, I mean, at a cellular level, it's essentially two NMOS transistors working in parallel. With that in mind, that means PUFsecurity builds on eMemory's bit cell technology and allows to adopt the same technology programming mechanisms, bit cell as NeoFuse. And with that in mind, we can take advantage of eMemory's wide and extensive platform availability, working with all major foundries and a few minor ones as well. Anyway, that's enough on the company overall. Really what we're here today is talk about security specifically. So I think as we all know, any connected device is exposed to all kinds of hacking and potentially threatening privacy and assets, but also life as well. And just to take a step back, or if you really want to do a rather scary and depressing trip onto YouTube, I think all of the three examples we have here are easily searchable, from a step-by-step guide to go through and hack a camera, all the way to watching a pretty terrifying example of someone cutting a car mid-journey. So that stuff's all there. But the one thing we don't really talk about within the industry as much is hardware security specifically, you know? And hardware attacks are a real danger, and they're a real thing out there. I mean, that same internet search can quite easily bring you to an Avida Tegra 2 being hacked for a Nintendo Switch as a hardware hack as well. And the three examples here, such as decapping with eFuse, to quite simply extract the key at that level, really doesn't need anything more than an SEM microscope, for example. Fault injection and differential power as well. I mean, admittedly, you're going to need an expert and you're going to need some expert equipment, but we've seen the videos of both of these real world hacks, and they're about 6 minutes long. It's something that really needs to be considered from day one. So there's fixes for this, of course, but we're talking about an invisible OTP and protection against side channel attacks and anti-tampering elements as well. But that's today. Really, what we want to do is also talk about the future as well, because within the industry, whether you want to talk about it as a metaverse or take your phrase of choice for what the future of semiconductors will involve, a step back makes it quite clear that more and more of our life is going to be defined by software. And in turn, that means a lot more devices, means a lot more various types of devices, and it means devices that need to last a lot longer. You know, when we think about the lifespan of a chip, we're often thinking about smartphones. We're thinking 2-3 years. It's a very different proposition when we start to think about cars with chips lasting 20+ years on the road. That's not just a threat and a consideration that's being held across the world right now with semiconductor companies. It goes all the way up to our customers. You know, this is something everyone is really taking quite seriously, that long-term security. So yeah, what does long-term security mean? And I think when we talk about the difference between hardware and software and the different varieties within the stack of solutions, I think it's important to understand what we're talking about here about security at the hardware level. The example we like to give, of course, is the idea of a lockbox with a key. You have that lockbox with a key providing encryption, perhaps for a website or an application. That key then goes to the operating system with an isolation techniques within there, to the firmware, and then onto the hardware as well. So lock key box, and it goes all the way through. The issue, essentially, and why we talk about the weakest link, is that software can be patched, software can be updated. This is a continually improving element, but hardware is much more static. And the problem at the hardware level is going to involve a tape out or a recall or some other possibly quite expensive element to try and remedy the situation. So we really want to begin to look at the hardware root of trust solutions from the very beginning. It's something that we're passionate about. It's something we want to encourage, hopefully everyone listening, to consider going forward as well. When we talk about hardware as well, it's not just hardware of trust, it's It's the cryptographic engine as well, securing the bus, all of these elements together. And I think the best way to start looking about that is to really begin with the boot up process with chips and key security. So we have the first generation of the several generations of how that has gone when we start to look at it. The boot process really began with conventional booting process as boot codes and a piece of flash without any security protocols at all. And the SoC would then request the code when booting up. So that was generation one. And then as we began to introduce some levels of hardware security into this, we began to encrypt. So the improved model encrypted the boot code, and then with a global key for decryption, that was injected into the SoC itself, protecting the firmware while the boot code is still stored externally. Today, though, we have a third generation. Secure booting. It's a little bit more in depth, and it has a series of stages. And I'll go through the stages in the next slide, but just for a brief overview here. It brings some of the boot code into the SoC specifically, so that the system can verify the authenticity of the flash during the booting up and later on. So, secure boot flow. Let's move on to that now. So the first stage, the bootloader, when it loads up the first code using ROM, the big issue here is, of course, the key storage and key generation from that first stage. Where is it being stored? How is the key being generated? When is it there? The second stage, which is then verified by the first, is typically done in OTP. The reason for that is flexibility, so that we can program the chip after manufacture. And from there, the same concept goes through the OS as well into the application layer. So you have that idea of the lockbox and the key, and you can see as that sort of verification process or key and decryption essentially ends up right back at the boot key at the hardware level. So as your application is running, if you want to create yourself a unique identity, it's dependent on that root key. It also means all of the security concerns, that point of storage and generation becomes critical, because that is the point which every other part is building this foundation of an ecosystem on top of, So that's why we talk about the four fundamentals of chip security. It's the main principles that we really look to develop our products, and it's also the things that we really want to encourage the rest of the industry to be aware of as well. The first being securing the OTP specifically, like I was mentioning in the boot code, usually around, and this is the sort of second form. And we have root key storage and root key generation during that first phase. And then we have the idea of a unique unclonable identification. So every single chip is verifiable and unique. So just to give you a bit more detail on those four, let's begin with the OTP. So I mentioned earlier a little bit about decapping and the threats involved with eFuse. I think this diagram kind of does most of the talking, to be honest. It doesn't really require much explanation, but the fact is when we're dealing with eFuse and moving on to an anti-fuse, like NeoFuse or NeoPuff, it adds that invisibility layer, so it eradicates that risk. The second part of that, where you're storing that OTP, can then be randomized as well, which is that sort of next phase. So I think one of the most significant advantages of using a secure OTP along with a PUF gives you that ability to scramble the address, storage location of the key. And the idea of root generation is the third in the principle as well. So a typical system that you'll see today injects the root key. So that's, of course, requiring injection at the CPUIP kind of process. And it requires a whole bunch of things, such as that external run number generator, a key database that needs to be secured as well, and not to mention the testing equipment. And per unit cost, we're talking upwards of up to about $2. So it's not insignificant costs, as well as those increased security risks. Whereas an inborn root key, such as ours, really eradicates almost all the external processes. There's nothing really in that sense. So we're getting that double win-win really of eradicating processes, making it cheaper, but also increasing the security, because you're never exposing the private key outside the SoC. As it's inborn, it's unique. And that is just perfect for the ideas and principles that are being adopted across the industry, such as zero touch, and the idea of zero trust right across the entire ecosystem. But talking about the ecosystem, I think I just want to come on to one of our last points here, in the idea of combining digital and analog solutions, because there's a lot out there. We're talking about the difference between. There's a lot of talk about hash and crypto engines, but the idea to create a solid solution really involves the combination of both analog and digital in that sense. So many types of root of trust solutions on the market, they'll address a few, but they won't take all of those, and they'll be usually an outsourced or a secondary IP to supply the OTP, for example, or the TRNG. So the idea of bringing all that together in one solution is the thing that drove us to really develop TopRT and Puff CC as drop-in solutions for everyone. So just to talk a little bit more about the detail, a soft IP typically includes from IP vendors things like a secure CP, crypto algorithms such as AES or hash, and a hard IP, which is process dependent. That's like we were just discussing, secure storage, root key generation, but also static and dynamic entries, as well as anti-tampering solutions. And that idea of the combination, I think, it's something that we're going to see, I think, much more in the future, because secure OTP is replacing eFuse. It's right now, and it's something that will only continue to become more widely adopted in the future. And a TRNG is, of course, that combination of digital and analog, which is required. So if you need a TRNG, you're going to need to, at some point, cross this chasm between the two elements of analog and digital. And with the idea of external key injection being that added process and that added cost, Puff having a zero-touch provisioning, that's, again, eradicating that. So increasing security and reducing overall cost. So that's enough talking about the theory. Let's talk about the products themselves. So I think these are the two ones we just want to talk about briefly, TopRT and Puff CC. The demonstration is with Puff CC, and we will move on to that in a second. But let's start with TopRT. It's our RISC-V certified hardware root of trust solution. So it involves the hard macros, secure OTP, TRNG for the entropy, the inborn key, of course, from the Puff, and a controller and secure boundary. There's two APB interfaces. The first one to the main bus, which is disabled after boot, and the second connects to your choice of secure subsystem. And for the RISC-V community, I mean, that really is up to you. And this is designed to be as flexible and universal as possible. The Puff CC is essentially taking the TopRT and then including our own crypto core processor. So that's a full suite of NIST certified crypto engines, as well as the secure boundary, of course, all put together. And the reason that that's appealable to a lot of customers, of course, it can unload a lot of the burden, secure operations from the CPU, and facilitate improvements right across the board with overall processing speeds. And you can extend the protection for real-time flash and encryption and decryption. Okay. Those extensions for flash, again, you can see from the diagram here, the XIP, for example. That's just the sort of suite of solutions we have. So although we do have these two distinct things in the market, we have a level of flexibility, and we have the expertise and team who just happen to be sitting next to me right now to help you go through that process. All right, I think it's time to move on to the demo. So let's move on to the demo. It's the Andes D25F CPU, like we discussed, with the A3 platform and Puff CC. So let's see if this video plays.
Together with Andes, we have made two boards, board A and board B. Each board consists of an Andes D25F with Puff CC crypto core processor and a piece of flash memory. The flash memory is encrypted by the local key within Puff CC. It starts the secure boot process as we powered it up. As you can see on the terminal, the zero-stage boots up first and verify. Then it starts loading the first stage boot code stored in the flash. Puff CC decrypts the code with its key for the core and to continue and finish the first stage boot. Upon completion, it enters the normal operation. We now switch in flash B into the board A and power it up again. As you can see on the screen, while zero stage still boots up successfully, the system holds as it cannot decrypt the first stage code, since Puff CC of each chip has its own unique key. So if the flash is switched, it will reject the switched flash and to protect the system.
Okay, I just want to close up this section and hand it back to John. Firstly, thank you to everyone for listening today. Thank you to John. And just to sum up, what we're dealing with here is a total hardware solution. So a secure OTP. It's an inborn identity provided by the Puff. It's TRNG compliant, and of course NIST certified crypto engine. So the Puff CC, Puff Crypto Coprocessor, has all of these elements put together, and that's what we're trying to share with the RISC-V community and everyone today. So thank you very much. I will stop sharing, and I'm going to let John jump in here. Thanks very much, guys.
So the PUFsecurity shared their solutions. RISC-V, just to let you know, a few slides for advertising from sponsor. RISC-V Andes cores are standard RISC-V cores with Andes secret sauce, Andes extensions. We added a few extras to make computing faster and more secure, just like technology called StackSafe. We have hardware-supported stack protection mechanism, so stack overflow issues. Power break and quick nap to save power. In fact, I see a typo here. Save power, or perhaps you want to change your CPU algorithm power signature, so you could change power of the pipeline. Lastly, we want to mention our ACE Andes custom extensions. You could create instructions to accelerate compute, or you could hide what operations you're doing. You could have custom memories and custom ports. And one way, this is the StackSafe, in that you record what your stack usage during the operation development. And then out in the field, if software acts funny, perhaps it's hacked, there's a stack overflow, it will generate an exception, and you could decide if you could continue to compute or do a reset. Make sure go back to the known firmware image. Power break, we mentioned. Under software control, I could change the frequency of the pipeline, how fast I compute. So if I could randomly change how fast I compute an algorithm, therefore I could hide my power signature. And it's under software control to divide up the clocks going into the pipeline. Lastly, we have this custom extensions. Now this, initially, a lot of people think about custom extensions, custom hardware. They think it's just to accelerate the algorithm. Well, yes, it does accelerate any algorithms by creating custom compute block, but we could do something else. We could create tight coprocessor interface, or maybe no coprocessor. Maybe we could absorb some of the PUFsecurity logic into a private bus, in that we could bring it to a private bus so that my data doesn't go over the main bus. So imagine keys stay on SoC, while keys stay in the CPU's private bus that has dedicated bandwidth, dedicated bus, so that you cannot see what's going on. And we could even hide it from the debug. So even in the debug section, you could hide the data that's going over. So really secure, protect the key, because I was just told that like HDMI keys are very expensive if it gets leaked. So you want to protect your keys, protect your system. So we are doing CPUs. We are working with experts like PUFsecurity to create system level solutions. And we're always innovating solutions to increase security and performance of our CPUs. So thank you for listening. And now time for some Q&A. We'll answer some questions. Jonah,
I thought Puff looked at physical characteristics of each individual chip. That true or not?
Well, yeah, it's true. I have a team of people around me, actually. I think it might make more sense to try and throw some of these questions to the experts here. But that one, yeah, that's a yes. Does anyone want to jump in?
Do you want to elaborate a little bit more on that? So Puff, you can look at it as a chip fingerprint for the device or the chip. And yeah, it has to do with physics. Our mechanism is quantum tunneling.
So yeah.
Yes. So
I mean, the Puff that it sends is an algorithm. Our option is we're moving it to the hardware, so it's
yeah, so like in our Puff, we use a natural variation of the process to determine a randomness in it. And then we use this randomness to assign either 1 or 0. So we give the chip a identity based on that. I know for many different Puffs, there's different mechanisms. There is the SRAM Puff, which uses the SRAM variation to determine the randomness. But in our way, we use 2 MOS transistors, and then there is a natural variation process. So it's like flipping a coin. So you get like a 50-50 chance of getting a 1 or 0, and then we use that number to assign the identity to the device. So basically, that's the physics behind our mechanism.
So everyone, that's another John. That's John sitting next to me here, just giving you a bit of an overview of some of the basics of it. Anyway, when it comes to the cellular level and the way that the Puff is enrolled.
So this looks like a follow-on.
Yeah.
Are the physical characteristics programmed into chips according to Andrew's technique that you described?
Yeah, so there's a process called the enrollment. So it's a process that we apply high voltage to the transistors and to determine, again, the 1 and 0. And then we use this to determine the identity for the chip. And so I think for our Puff, we actually have a paper in 2018. We won the ISS CC Best Paper Award.
That's
and
correct,
yeah, and I think that is public information. And there's a lot of detail on the mechanism on there. Yeah, we should be able to share that paper.
Yeah, that's no problem. Yeah. Let's move on then. Let's move on to the next question.
All right, so talking about ARM as kind of like the standard for most security in these systems, how does the solution from Andes and PUFsecurity compare? And
so, well, of course, it's the trust zone. I mean, the thing about the trust zone, we're talking.
So I think just to give a simple answer, we talk about the Puff CC, right? I'm sure people are familiar with the crypto cell. So Puff CC basically is just like the crypto cell 312. So if you're familiar with CC 312, then you just use a different subsystem, and then you apply the Puff CC into the RISC-V subsystem, and that basically replaces the crypto cell. Yeah, just from a simple answer.
okay. What other cores besides the one that was shown in the demo is PUFsecurity working with? What other Andes cores?
I think for this one, we have a demo. This is mostly for IoT product. And there's another core, I think, for more leading nodes. It's maybe John Min can help me on this. I think I forgot the part number on that one, but it's NX27.
Right. So the simple answer is our CPUs are flexible. PUFsecurity's solutions are flexible. So we could match any of the PUFsecurity's security solutions to any of our CPUs. Our CPUs support all the standard buses, standard interfaces, PUFsecurity as well. So we have the D25 which is our mid-range family, NX27V, which is our high-end vector processor, as an example of what you could achieve. But certainly, you as an end user could pick and choose the right security solution for the right processor. And integration is, most of the integration is done. We'll help you integrate it to optimize the bandwidth.
Yeah, it's relatively straightforward when we talk about moving between the two options. So it's mainly clock frequencies and a few other elements that need to be adjusted individually. But that's really it. And the whole process we setting up TopRT and Puff CC was for exactly that idea of flexibility and really playing into the RISC-V community in the sense that we have elements that can really plug and play with a lot of different options and a lot of different customers and partners like Andes.
How does the Puff security solution deal with multi-core designs?
So I think for this question, it should be the same because usually there's just one core dedicated to the crypto, and then no matter if the design is multi-core or single core, we still just use the same IP to support it. Yeah. So through our interfaces, which is customizable, and I know Andrew showed APB, but we can also do like TCM or tile link for other subsystems. Yeah, like RISC-V.
Yeah.
Okay, I want to put security in a system. So how much bandwidth am I going to consume by putting this security into a system?
So I think this depends on the complexity of the task, and we're pretty flexible on that. We can support like I guess in different levels of security requirements. Yeah,
it's very project specific. It's hard to give a general number, but
very task specific, right? I mean, like for example, if the capacity is very high, so it consumes like more time. So you can either speed up the engine, the crypto engine on hardware level, or the on the core level to wait a little bit longer. So it, like John just mentioned, it really depends on the kind of task, and we actually will help the customer specifically based on their scenario.
Yeah, so it's kind of like a trade-off between security and performance. So it depends on the application. Yeah,
and that's why we have the Puff CC as well as the Puff RT. It's the idea of flexibility in the sense that if you are looking for whatever level of security, but also the particulars of that problem at hand, you know, if it is space or it's area we're talking about, either one, we can add a level of flexibility to it in that sense.
So secure boot was what was in the presentation. Is there other examples of where Puff security and Andes solution would work, or give us an example, I guess.
So I think when we're looking at security, it starts from the secure boot, but then it's a chain of trust. So like the Puff CC, we have the OTP in it, right? So that's why it's important for a secure boot, because in secure boot, there's a requirement of boot code storage, and the OTP brings in the flexibility. And starting from there, all the way to how we use the Puff to generate the key, and then provide the important primitives from the hard macro, then we integrate them with the RTL, the crypto engines, and then with Andes CPU. So it's kind of like just a one-stop shop solution for our customers. So they get process qualified hard macro, and then all the way to soft macro with Andes.
So in actual usage scenario, it also supports like secure update and other security functions like lifetime management in actual usage scenario. I think that's what some audience might be interested about. So if you want more detail, feel free to contact us.
Yeah.
So the last question I have is the security requirements for individual markets. So automotive would probably have a higher level of security requirement than, say, consumer. Or is there kind of some way of listing the levels of how much security you want to add for individual applications?
I think this is an issue that's right across, not just us, everyone. The fact is, when it comes to standardization, particularly for the IoT, there's a lot out there, and I wouldn't say there's any kind of set rules that have really sort of dominated. It's getting there. It's getting there, we could say. And I think the fact is that RISC-V and other communities are beginning to take steps forward to really try and bring it all together. And then we're beginning to see a correlation, but it's not quite there in terms of set standards. For the automotive industry, yes, there's definitely a few that are non-negotiable, which we have gained certification for. But do you guys want to jump in with any of the details?
Yeah, I think for automotive, there are safety factors, but it's different than security. I think for security, it's the same because for every secure system, you need a key and you need storage, you need entropy, and then you need cryptos to run your crypto operations. So no matter what application you're going with, the fundamentals of hardware security is still a requirement. Yeah, and then you just look at different standards when you go to different applications. That's another thing.
Okay, another question just came in. NIST 800-90B, recommendations for entropy source used for random bit generation, and NIST 800-22, a statistical test suite for random and pseudo-random number generators for crypto applications. Does Puff need to pass these two criteria and more?
So we're compliant with both of those suite, and since we're from an IP level, so we did the testing on that. But from a product perspective, I think the product will have to go through a product certification. So that would be our customers, but our IP definitely supports those suites. Yeah.
Okay. Next question. How can you guarantee the stability of the Puff output with temperature variations and with aging effects?
Okay, so I know Andrew didn't show much data here, but actually for our Puff, we have quite a few silicon data with different foundries from advanced processes all the way to mature processes. And just based on the bit error rate, we have a 0-bit error rate. So unlike other Puffs where you need helper data to fix that. So through different voltages and temperature, we prove to be reliable because our bit error rate is always 0. So I think that's one of the key benefits.
Sure, not a problem. And we're trying to keep this presentation as light as possible in technical detail. It's actually great that we're getting these answers, and we're happy to follow up offline. Anyone can come and give us more detail when it comes to a more technical overview of how the Puff works, some of the standards and the sort of parameters of what we're talking about. We have all that data ready to go. Maybe not on a 20-minute introduction, but this is making us all pretty happy to get questions like this today, for sure.
All right, one last question. This is the last question.
Sure.
Security for IoT devices in industrial manufacturing environments. Can you make a comment?
So I guess you're talking about a certain temperature requirement.
Yeah.
So I think we follow the foundry process, and we have the characterization reports and qualification reports based on that. But I think usually we go beyond that temperature just in real situations.
Basically, if we want to talk about those details, the temperatures we're discussing where we have issues, it's basically the complete destruction of the chip. Anyway.
Yeah, and
so it's within those parameters.
Yeah, and we also had radiation hardened tests, and we have different tests in different harsh environments. So yeah, I think we can meet that standard.
Oh yeah, sure.
So any last minute comments, Andrew?
No, just thank you to John, thank you to John, and thank you to everyone for giving us this chance to share some of this information. Yeah.
John,
Yeah.
any last words?
Well, thank you for attending this. Your questions have given us an idea for the next webinar.
Yeah, I hope so.
I will work with Andrew and the Puff team. Perhaps we'll do another one and go into deep dive into one of these specific areas. It's kind of it's interest area for me, and it's definitely interest area for my customers. And Puff solution delivers a good solution. So thank you very much for joining us this evening, and we will post the video and the slides shortly. We'll notify you via email when you registered. Yep. So thank you very much. Have a great evening.
Thank you. Bye, friend.
Bye.
Bye.